Welcome back to AI Peer Review. Today we're diving into, well, a really fundamental question about large language models.
Yeah, it's something that's been bubbling under the surface for a while.
Exactly. How much of the amazing reasoning we see, in math, coding, that kind of complex stuff, how much is actually learned during post-training versus how much was sort of already there, just latent in the base model?
It's a huge question, practically speaking. I mean, think about the compute we spend on fine-tuning. If those capabilities are mostly latent, are we maybe overdoing it on the training side?
Right, and we're digging into an intriguing paper today that tackles this head-on. They propose something called power sampling.
It's a training-free technique, purely done at inference time. And the claim is it gets reasoning performance that's comparable to, sometimes even better than state-of-the-art reinforcement learning methods.
Which is kind of wild because RL, especially RL with verifiable rewards, RLVR, that's been the dominant approach, right?
Absolutely. Methods like GRPO group relative policy optimization, they're everywhere for boosting performance on benchmarks, like MAT 500. They work empirically.
But they're expensive. So much data, reward models, tuning.
Exactly. And that success led straight to this debate we mentioned. Is RL actually teaching the model new reasoning pathways? Or is it just aggressively sharpening the probability distribution the base model already had?
So basically just amplifying the good stuff that was kind of hidden in there anyway.
Precisely. Is it finding near gold or just polishing the gold that was already mined? And there's evidence pointing towards sharpening.
Okay, let's unpack that evidence, maybe starting with RL's main drawback, beyond the cost.
Right, the cost is one thing, but the diversity problem.
Right.
That's key here. RL definitely boosts single-shot accuracy. Your first answer is more likely to be right.
Yeah, we see that in the benchmark.
But if you look closely at the reasoning traces, the step-by-step solutions that these RL models produce, studies show they often have a high likelihood under the original base model.
Ah, so the base model could have generated them, it just wasn't as likely to pick that path first.
Kind of, yeah. RL seems to be acting like a very effective filter, pushing the model towards those pre-existing high-quality sequences.
But what's the cost? You mentioned diversity.
Yes, the diversity collapse. It's becoming a well-documented issue. While that first shot, pass at one, gets better, the ability to generate multiple different correct solutions really suffers.
So if you ask for a second or third way to solve the problem,
Performance drops off a cliff. You measure this with pass at k, scores the probability of getting a correct answer within k attempts. For RL models, that curve often flattens out dramatically after K1.
it's like the model becomes fixated on one way of solving things. It
Yeah.
loses its exploratory capability.
Exactly. It trades multi-shot potential for single-shot perfection, or near perfection.
Okay, so the goal then becomes, can we get that RL-style single-shot boost, that sharpening effect, but without the training cost, without needing a verifier, and crucially, without sacrificing that diversity?
That's the million-dollar question this paper tackles. And their core idea is pretty elegant, actually.
Which is?
If RL is basically just sharpening the base distribution, px, why not just define a sharper distribution mathematically and sample from that instead?
Okay, so skip the RL middleman. How do they define it?
They propose sampling from what they call the power distribution. You take the base model's probability for a sequence, px, and you raise it to a power, alpha, where alpha is greater than 1. So you sample from alpha.
2 to the alpha. Okay, so sequences that already had high probability under the base model get amplified a lot, and low probability ones get squashed even further down.
Exactly. It's explicit mathematical sharpening. But, and this is important, it's not the same as just turning down the temperature during sampling.
Right, I was wondering about that. Low temperature sampling also uses exponents, doesn't it? How is P alpha different? This seems like a key technical point.
It absolutely is. We need to get into the weeds a bit here. Standard low temperature sampling modifies the next token probabilities at each step.
Okay, so it's local, step-by-step decisions.
Right. Mathematically, it ends up being like an exponent of sums of probabilities of future paths. It tends to favor tokens that lead to many possible completions, even if each individual completion isn't super high likelihood.
Sort of averaging out the potential futures.
Kind of. Whereas sampling from alpha involves, conceptually, exponentiating the likelihood of the entire sequence first. This leads to a different mathematical form, a sum of exponents.
A sum of exponents versus an exponent of sums.
Okay.
What does that mean in practice for generation?
It means alpha favors tokens that lead to few but extremely high likelihood future paths. It's looking for the single best peak outcome, not the average outcome.
Ah, I see. So it's less likely to get sidetracked by options that look okay initially but don't lead anywhere great.
Precisely. The paper calls this avoiding negative pivotal tokens. These are choices, maybe early in the sequence, that look promising if you're just being greedy or using low-temp sampling.
But they actually lock you into a path that overall has a very low probability of being correct or high quality. A dead end, basically.
Exactly. Pelfatol, because it's biased towards maximizing the total sequence likelihood, inherently steers away from those traps. It encourages a kind of implicit long-term planning.
That makes a lot of sense for complex reasoning tasks where one wrong turn early on can ruin the whole thing.
Okay, so conceptually, Pelfatol is powerful, but how do you actually sample from it? You can't calculate that normalizing constant, right? It seems computationally intractable.
You're spot on. Direct sampling is impossible. So they bring in a standard tool from statistics, MCMC, Markov chain, Monte Carlo.
Okay, MCMC. Specifically, Metropolis Hastings, I think the paper mentioned.
That's the one. MH lets you generate samples that approximate a target distribution like Palfatol, even when you don't know the normalizing constant. You just need to be able to calculate the ratio of probabilities between two states. But MCMC, that sounds iterative. Doesn't that mean we're just shifting the computational cost? We avoided expensive training, but now we have potentially expensive inference.
That's the trade-off, absolutely. They implement it using what they call autoregressive, MCMC. It doesn't redo the whole sequence each time. Instead, it works in blocks.
Blocks, like chunks of the sequence.
Yeah. For a sequence of length, say 3,672 tokens, they might work with blocks of size 192. In each MCMC step, it proposes resampling a random block using a proposal distribution.
Like maybe just the base model itself?
Could be, or a slightly modified version. Then it calculates the Metropolis-Hastings acceptance ratio based on how the likelihood under Palfa changes with the proposed new block versus the old one.
And you repeat this process how many times?
That's the knob you can turn. No MCMs, a number of MCMC steps. Maybe you run it 10 times. More steps generally means a sample that better approximates the true alpha distribution, but it costs more compute at inference time.
So we've traded a huge fixed upfront training cost for a scalable inference cost. You can decide how much compute to spend per generation to target higher quality.
Exactly. More MCMC steps equals potentially better alignment with that ideal sharp alpha distribution.
Okay, the theory sounds plausible, the implementation clever. Let's get to the results. Does this training-free inference time method actually hold up against the heavyweight RL champ GRPO?
The results are, well, they're pretty compelling. Let's look at Table 1 in the paper. They tested across different models, like Qwen 2.5 Math and Phi 3.5 Mini, and different tasks.
Start with Math 500. That's like GRPO's home turf, right? It's
Right.
often trained specifically for that.
Right, and power sampling performs remarkably well there. For the Qwen Math model, GRPO gets 0.785 accuracy, power sampling, 0.748.
Wow, okay, that's really close. Essentially neck and neck, considering one involved massive training and the other didn't.
Exactly. It strongly suggests that GRPO wasn't really adding much capability beyond what power sampling could elicit from the base model just through better sampling.
But what about out of domain? That's where RL methods sometimes falter if they've overfit. How does power sampling do on, say, human eval for coding?
This is where power sampling really shines and validates the latent capability idea. On human eval, using the Phi 3.5 Mini model, power sampling achieved middle 0.732 pass at 1.
Okay. And GRPO.
GRPO scored 0.134.
Whoa. That's not even close. A massive difference.
It's huge. It strongly suggests GRPO overfit to its math training data and verifier, potentially damaging the model's general coding ability. Power sampling, by just sharpening the base model's inherent distribution, retained that general capability much better.
And it wasn't just coding, right? They tested on general helpfulness, too.
Yes, AlpaCaival 2.0, which doesn't have easy verification. Power sampling consistently outperformed GRPO there as well. It seems more robust across different types of reasoning tasks.
Okay, so single-shot performance is comparable or better, especially out of domain. What about the diversity issue? Did power sampling fix the pass at K problem?
This is probably the most significant finding, illustrated well in Figure 5. The pass at K-curve for power sampling isn't just better than GRPO for K1, it's often better than the base model too.
So not only does it match the high pass at 1 of RL, but it also maintains or improves the multi-shot ability.
Exactly. Unlike GRPO, where the pass at K-curve typically shoots up for K1 and then immediately flattens, power sampling shows sustained improvement as K increases. It successfully delivers high single-shot accuracy without collapsing the solution diversity.
That feels like getting the best of both worlds. You get the sharp first answer, but you retain the ability to explore alternatives.
Precisely. It directly addresses that long-standing weakness of RL post-training.
Did they look at why it works? Like, does it actually target high likelihood regions as intended?
They did. Figure 4 shows analysis confirming that power sampling does indeed steer the generation towards sequences with higher likelihoods under the original base model. It validates the core mechanism.
So the base model does know best. In a sense, you just need a better way to ask it.
That seems to be the implication. Interestingly, they also found power sampling naturally produces longer reasoning traces, similar in length to GRPO, even though there's no explicit reward for length.
Suggesting that longer, more detailed reasoning might just be correlated with those higher likelihood solutions in the base model.
Plausibly, yes. Now let's revisit the cost. We said it shifts cost to inference. How much?
Yeah, that NMCMC $10 setting. What's the damage?
The paper estimates the inference cost multiplier is about 8.84 times the number of generated tokens compared to standard autoregressive sampling.
Okay, nearly 9x inference cost. That's not trivial. You definitely pay for the quality increase at generation time.
Definitely not free. Yeah. But you have to compare that 8.84x inference cost to the total cost of an RL pipeline.
Right, which includes the initial RL training, data collection, reward model training, hyperparameter tuning, potential stability issues.
And the need to potentially retrain for new domains or tasks. The power sampling cost is paid per query, but it avoids that massive, complex, and often brittle development cycle. They estimate the cost is comparable to maybe one epoch of GRPO training, but without any of the setup.
That puts it in perspective. It's a different cost model, potentially much more flexible and cheaper overall, especially if you don't need peak performance on every single query.
And the method seems pretty robust. They show in Figure 6 that while alpha equals 4 might be optimal, performance is pretty stable for alpha values of 2 or more.
So you don't need to spend ages tuning alpha.
Seems not. And performance clearly increases with more MCMC steps, up to around 10 where it starts to level off a bit, showing the iterative refinement works as expected.
Okay, let's try to synthesize this. What's the big takeaway here?
I think the main message is that a surprising amount of the reasoning capability we attribute to expensive post-training like RL might actually be latent within the base models themselves.
And power sampling provides a way to unlock that potential purely through a more sophisticated sampling strategy at inference time.
Exactly. It reframes the problem, at least partially, from a we need better training problem to a we need better sampling problem.
Which is huge, especially, as you mentioned, for domains where you just don't have a good reward signal or verifier for RL.
Right. Think about open-ended creativity, complex scientific reasoning, areas where defining correctness is hard. Power sampling doesn't need that external verifier. It relies on the base model's own internal likelihood estimates.
So it generalizes better, avoids reward hacking.
And potentially saves a ton on development and training compute.
It really makes you question the return on investment for some of these complex fine-tuning pipelines. If power sampling gets you 95% of the way there with zero training, that changes the calculus.
It certainly does. It shifts the focus towards understanding and leveraging the inherent capabilities of these massive base models.
So here's the provocative thought to leave you with. If so much performance gain, particularly general reasoning ability, can be unlocked just by finding the high likelihood paths the base model already knew about, how much of the massive effort poured into RL post-training is truly teaching new skills versus just being a very, very expensive way to filter outputs the model could already generate, albeit less reliably? Something to definitely mull over next time you're designing that model pipeline.